Hey everybody, Mr. Judson here. So this video I'm making from home instead of at school. I just didn't get it done on Friday. But what we want to do is we want to talk about this thing called the first derivative test. Okay? And when we say first derivative test, what it does is it looks at the slope of a tangent line. So here's a curve. I've got this tangent line here. And what we should notice is that as I move this tangent line around, the slope is positive everywhere up till I get to this point right here. Okay? Also, as I work left to right, we talked about this last year, this function is increasing. Okay? I think there was even a question on the Central Washington test that dealt with that. And then from this point to this point right here, our relative maximum to our relative minimum, then the function begins to decrease. And when it's decreasing, this tangent line has negative slopes all the way down to this point right here. And then from that relative minimum on, my tangent line now has positive slopes again, all the way off to infinity. So what we want to get from that is this. If f prime of x, our derivative, is negative, then f of x is decreasing. Okay? That's what's happening from this point right here down to here. Our derivative is negative, which means the slopes of all the tangent lines are going this direction. And that happens where the function is decreasing. Okay? If f prime of x is positive, then f of x is increasing. And that's what happened from this point all the way up to our relative maximum, and also from this relative minimum off to infinity. Function is decreasing, and the slopes of our tangent lines, when that happens, are going to be positive. So what we're going to do is we're going to use this as a way to help us graph a function. Okay, and we're going to have to set up a procedure on how we do that, but this is the main idea right here. So this thing we're going to use that's called the first derivative test, there's a series of steps that we want to go through. And really, this is all about trying to decide, is my function increasing or decreasing? Okay? Is f of x increasing or decreasing? That's what we're doing with the first derivative test. So our first step is we need to find the critical numbers. And you know, we said in our last video that this happens when f prime of x equals 0 or undefined. Okay? Where is the derivative undefined? Not the original function. There's a difference there. So that's the first thing I have to do, is find all my critical numbers. The second thing I need to do is to create intervals. And these intervals are really from negative infinity to positive infinity. Unless certain numbers don't fit the domain. If I've got a square root where, you know, maybe I got to make sure that we're getting something positive inside, you know, you could say we're going to go from 0 to infinity, but I got to break that down into intervals as well. Okay? Once I have my intervals, then I want to choose a test number, and then we're going to check the sign of f of x. And you know, we just said a second ago that when we look at f prime, if it's positive, that means my function's increasing. And if the derivative is negative, that means my function is decreasing. So it's this sign that's going to tell us what's happening to the function. And then our last step is to either pick increasing or decreasing for the function f of x. And there's a way that we're going to set this up. What we're going to do is we're going to draw a table. You guys you'll hear me say this all the time, make the table. Okay? And when we make this table, it's going to have 4 rows in it. We're going to start with intervals. Once we have intervals, we're going to have a test number. Then we're going to check the sign. And then we're going to draw a conclusion. Okay? And then we'll have all these different intervals where we do this. But this is the table that we're going to make every single time we do the first derivative test. And it's one of those things where I don't want people to try and come up with their own way of doing this. This is the way that everybody who learns calculus does the first derivative test. Okay? So if somebody let's just say somebody moves to Virginia in the next week, and you're talking about the first derivative test, they should be doing it the same way we're doing it here, right? All right, let's do a practice problem. All right, so we'll start with something easy here. They're asking us to find the intervals where f of x is either increasing or decreasing. Now, when you guys look at this function, we all know what this looks like, right? It's a parabola. And so it's going to be decreasing down to the vertex and then increasing after that. So I kind of already know what the answer looks like, but I want to get used to this procedure, okay? So first thing I need to do is I need to take the derivative. So y prime is going to equal 2x plus 8. And then I'm going to set that equal to 0 to find my critical numbers. So 2x plus 8 equals 0. If I move 8 over, it becomes negative. Divide by 2, x equals a negative 4. That's my critical number. And it's not undefined anywhere. Okay? There's no way to make the denominator equal 0 here. So this is my only critical number. So when I set up my intervals, I usually just abbreviate that int. I'm going to have an interval that goes from negative infinity to negative 4. And then my next interval goes from negative 4 to positive infinity. Something that we did last year that kind of is similar to this was when we solved inequalities. Do you guys remember doing that? We set the thing equal to 0 and factored it, and then we'd call those our critical numbers. And then what we'd do is in each interval we'd make a test number and check it to see if it was greater than 0. Remember that guy? He goes, no. That's very closely related to this. Okay. All right. So let's see. Now I have test numbers. So you can pick any number you want. It just needs to be in the interval negative infinity to negative 4. Seems like the easiest one would probably be negative 5. And the easiest number in this interval, probably 0. Although some people might think 1 is pretty easy. All right? And then we're going to plug it back into the first derivative and check the sign. Okay, so remember, it's if the derivative is negative, that's where we're decreasing. And if the derivative is positive, that's where we're increasing. So I'm going to put negative 5 back into the derivative here. I'm going to get a negative 10 plus 8, that's a negative value. If I plug a 0 in, I get positive 8. And so now our conclusion, I usually abbreviate that too. Negative means we are decreasing. Positive means we are increasing. Which we all knew, this thing looks like a parabola. We knew we were going to start off decreasing and then increasing. So negative 4 must be where that vertex is. Okay, so now I would say that this function is decreasing on the interval negative infinity to negative 4, and it is increasing on the interval negative 4 to infinity. Notice how I didn't use a bracket here at negative 4, and the reason for that is here's my tangent line again. As I come along this parabola, I get to a point right here where it's neither increasing nor decreasing. It's horizontal. That's right at the number -4. So if it's horizontal, I can't really say that it's decreasing there. It's kind of neutral at relative maximums and relative minimums. Okay? All right, that's it. That's our answer for this problem. We're just trying to figure out where a function is increasing or decreasing. By the way, just so you guys know this, probably the number one thing out of Chapter 3 is to build some tools that will help us graph an equation without using our calculator. And this is part of that, right? If I want to produce the graph, I know it's decreasing in the beginning and then it's increasing. So I know it's going to look something like a parabola. All right, let's try another one. All right, you guys go ahead and try this one. We've got y equals x cubed minus 3/2 x squared. And we want to figure out where is this function increasing or decreasing. You guys go ahead and try it. All right, so to get my critical numbers, I need to take the derivative. So I've got 3x squared. Derivative of this, when I bring the 2 down, I get 6/2, which is just 3x. And now I need to factor that. So I'm going to factor out a 3x, and what I'm left with is x minus 1. If I set that equal to 0, that means my critical numbers are at x equals 0 and 1. It's not undefined anywhere, so we're okay there. So now we set up our table for the first derivative test. I need intervals. I need a test number. Whoops. Test number. We're looking for a sign. I'm always looking for a sign. And a conclusion. All right, so we're going to go from -infinity to 0. And then we're going to go from 0 to 1. And then from 1 to infinity. Now, you guys, let me just say this again. Every year, people try to simplify this table and make it into less than it already is. It's already been simplified down as far as it can go, okay? Please do this every single time. Draw out the table, write everything in here. Make sure you tell me what each column or each row represents. You know, like I said, this is a method that every single teacher across the country recognizes. We don't want to come up with our own method that all of a sudden I'm looking at going, what is that? I don't even know what that means, okay? So please, let's stick to this format right here. All right, my test numbers, so I'll choose -1 here. Here I'm going to choose 0.5, and here I'll choose the number 2. So when I plug these back in, you can plug it into the original derivative if you want, but the factored form is always going to be a little bit easier. Right? If I plug a negative in here, I've got a -3 and a -2. Negative times a negative is positive, so I know we are increasing right here. And then if I do 0.5 times 3, that's positive. Put a 0.5 here, subtract 1, that's negative. Positive times a negative, that's negative. So we are now decreasing. And then plug in a 2. Positive 6, positive 1, positive times a positive, and we are increasing again. I don't really care what the answer is, I just want to know what's the sign of the answer. So I want to make that as easy as I can. So this function, y, is increasing on the interval -infinity to 0 and 1 to infinity. And y is decreasing on the interval 0 to 1. So the moment you see this right here, you know that your function's going up, then it turns and comes down, and then it turns and goes up again. All right? There's my answer. Let's try another one. All right, you guys go ahead and try this one. All right, first step, I got to find the derivative so I can get my critical numbers. And so what we have here is a product rule. And I suppose if you wanted to, you could go ahead and multiply this thing out. I'm not sure which way would be faster. I'm just going to go do the product rule and we'll see what happens. So I'll take the derivative first, which is a chain rule. So I've got 2 times x minus 1 to the 1 power times the derivative of the inside, which is just 1. And I want to multiply that times the second piece. And then plus, leave the first piece the way it is, x minus 1 squared, and take the derivative of the second piece, which is 1. And so when I look at that, I see I could factor an x minus 1 out of each of these. What I'm left with is 2 times x plus 2. So that would be 2x plus 4. And I took, oops. So I got 2x plus 4. And then when I take x minus 1 out of here, I take 1 out, I'm still left with 1. So x minus 1. And then if I add my like terms together, I would get x minus 1 times 3x plus 3. And so when I set that equal to 0, my critical numbers are 1 and negative 3 over 3, which would be a negative 1. So x equals plus or minus 1. All right, so now I'll make my table. I've got intervals, I've got a test number, we're looking for a sign, and then we will draw a conclusion based on that. So my first interval will be from negative infinity to negative 1. My next interval from negative 1 to 1. And then from 1 to positive infinity. So again, when I say don't get lazy and try and make this less than it is, sometimes people don't put the parentheses in here. And if you don't put the parentheses in, then it's not really an interval. It's just a list of numbers. Okay, so we want to make sure we write those intervals down correctly. All right, so a good test number here would be negative 2. A good test number in that interval would be 0, and here a positive 2. And I think the easiest thing to plug it back into is probably this piece right here. So if I plug in a negative 2, I'm going to get a negative value. Here I'll get negative 6 plus 3, that's negative, so a negative times a negative is positive. So we are increasing. If I plug in a 0, I get negative and positive, so that's negative. Here we're decreasing. And here if I plug in a 2, I'd get positive and positive. That's positive overall, so we are increasing again. Now, somebody could have said, look, Judson, I know that when I square this, I'm going to get an x squared term. Times this, I'm going to get an x cubed term. So I know that this up here equals x cubed plus something. And I also know that a cubic always looks like this. So to me this was all a waste of time. I already knew it was increasing, then decreasing, then increasing. Which I would say, what are you going to do when you get to the harder problems? Because we're doing the easy stuff now so that we can learn this procedure and understand it. Once we get to a harder problem where we don't recognize what the curve looks like, this is going to tell us what it looks like. All right? That's why it's so important to make sure we do this procedure the way we're supposed to. And what happens when we get into natural logs and exponential functions, e to the x? We got to be able to do this stuff there too. All right? All right, so my answer here is that this function f of x is increasing on the interval negative infinity to negative 1 and 1 to infinity. And it is decreasing on the interval -1 to 1. There's my answer. All right, we got one more to try. Oh yeah, there we go. That's what I'm talking about. Now we're getting to something that's a little more complicated, okay? So we got to make sure that we can work through this process. Before we even start this one though, there's a bit of a domain issue. You know, when I look at this, I see a square root. The stuff that's inside the square root has to be positive. And so when I look at this thing, I'm thinking, okay, let's see, 9 minus what? You know, I want to keep this positive. Like if x was a 2, 9 minus 4, that would be 5. Square root of 5, we can do that. That's okay. If x was a 6, square that, you get 36. 9 minus 36, that's some negative number. I can't take the square root of that. So I think what happens here is our domain is going to be any number between -3 and +3. Right? Because at 3, when I square it, I get 9. Same thing at -3, so 9 minus 9 is 0. I'm okay there. On the number line, if I go anywhere outside, let's just say this is 3 and this is -3 here. If I go anywhere outside of this number towards -infinity or anywhere larger than 3 here, this function doesn't work. So in my table, I'm not going to go from infinity to something. I'm going to go from -3 to something and then to something else. I'm going to end at +3. Okay, you guys go ahead and try that. Alright, so when I do the derivative, I'm going to think of this as 2x times 9 minus x squared raised to the 1/2. I've got another product rule. So I'll take the derivative first, which is 2, times the second piece. I'll just go ahead and leave that as a square root. Plus, leave the first piece the way it is, and take the derivative of this. So I got to bring that 1/2 down in front. I still have 9 minus x squared. Subtract 1 from the exponent, I get -1/2. And then times the derivative of the inside, which would be a -2x. And so that means I now have 2 times the square root of 9 minus x squared. Let's see, positive times a negative, so that's negative overall. This 2 right here will cancel with this 2. And so what I'm left with is 2x squared. Because it's a negative exponent, I got to drop it below the fraction bar. And so that becomes the square root of 9 minus x squared. So I want to know, where does this thing equal 0, or where is it undefined? Well, to do that, I think I'm going to just try to get one fraction here and get a common denominator. So if I multiply the denominator by 9 minus x squared, I got the square root of. I got to do the same thing up here, 9 minus x squared. And so now what I have is square root of 9 minus x squared in the denominator. When I multiply these two, I just get what's inside. But then I got to multiply that times 2, so I'm going to get 18 minus 2x squared, and then minus this 2x squared. Which means I now have 18 minus 4x squared over the square root of 9 minus x squared. So I've at least gotten this down to a single fraction. And the reason that's important is because the only way a fraction can equal 0 is if the numerator equals 0. Right? If I came over here and said, okay, what would it take to make this equal 0? Well, now I've got 2 terms and I'm going to have to do a little more work. We could still do it that way, but I think this is a little bit easier. All right, now, undefined, at -3 and +3. So undefined at x equals ±3. That's the endpoints of our domain here. Okay, so that really doesn't affect a whole lot. When I take this and set it equal to 0, let me come over here and do that. 18 minus 4x squared equals 0. I'll move the negative 4x squared over to this side. And then I'll go ahead and divide by 4. So I get 18 fourths equals x squared. I could reduce this fraction, but the reason I left it in fourths is because I know I'm about to take the square root of something, and the square root of 4 is 2, and at least I don't have a square root in the denominator. It doesn't really matter to us. I don't care if it's in the denominator, but that's kind of why I stopped there. So x equals plus or minus the square root of 18 over square root of 4 is 2. This would be 2 times 9. The square root of 9 is 3. So what I really have is 3 root 2 over 2, plus or minus. There's my critical numbers. Now, exactly what is that number? I don't really know. So let me get a decimal. I think we want to know what that number is. Maybe it doesn't matter. Let's make our table. So I've got intervals. I want a test number. Looking for a sign, and we're going to draw a conclusion from that. All right, so we're starting at -3. There's a parenthesis there, so I know x isn't going to equal -3 because it's undefined there. And I'm going to go to 3 root 2 over 2. I still don't know what that is. And then I'm going to go from negative, sorry. And then I'm going to go from negative 3 root 2 over 2 to a positive 3 root 2 over 2. And then I'm going to go from 3 root 2 over 2 to positive 3. There's my intervals. So I know what the test number is here, but I don't know what this is equal to, so I guess I'm going to have to find that out. There's what I get. So it's about 2.1, well this will be negative, 2.121. So if I go negative 2.5 right here, I should be okay. And over here I'll go positive 2.5. And so when I plug that back into my derivative, I think the best place to plug it in is this right here. If I plug it in here, I'm going to actually have to find each individual answer and then subtract that and then see what I get. But if I plug it into this, all I have to do is check to see, do I get a positive divided by a negative? Do I get a negative divided by a negative? You know, what happens with that fraction? And by the way, our denominator can only be positive, right? We've already said the domain is between -3 and 3, and that's to guarantee that we get a positive number inside the square root. So no matter what, it's going to be something divided by a positive. So really the numerator is going to tell me what sign to put here. If I plug in a 0, that'll be 0. I've got 18 over some positive number. So that's positive. All right, so I'm going to plug a 2.5 back into this numerator. And so what I've got here is 18 minus 4 times a negative 2.5 squared. And I got a negative 7. So that means this is negative right here. When I plug a positive 2.5 in, same thing's going to happen that happened here. When I did a negative 2.5 times a negative 2.5, I got a positive result. And then times 4 and then at 18 minus that, so this number must be larger than 18. If I put a positive 2.5 in there, the same thing's going to happen, so that's also negative. So we are decreasing, increasing, and then decreasing. So this function f of x is decreasing on the interval -3 to -3 root 2 over 2, and 3 root 2 over 2 to +3. And we are increasing on the interval -3 root 2 over 2 to a +3 root 2 over 2. All right, now we still got to talk about, why are we even doing this? Like, how is this helpful to us? How does this help me produce a graph? And that'll come in our next video. For right now, all we want to do is just be able to figure out if a function is increasing or decreasing and make sure we understand what that means. Right? So if I was to graph this function, it starts off decreasing, then it increases, then it decreases. I believe, I've seen this before, if this is -3, we are decreasing, then increasing, then decreasing. This would be +3 right here. So I would have a relative minimum here, relative maximum there. Okay? But the graphing part is coming later. Right now we're just trying to find the intervals. All right, you guys, that's it. That's all I have for today. Let me get you a homework assignment. All right, so here's our homework assignment for tonight. Not a super long assignment, but these problems aren't quick either. They take a little bit of time to get through. So we're on week 14. This is our Monday piece. And we're on page 187. And we're going to do number 6, number 8, and then 11 to 14. All right, you guys, that's it. Stay safe. Let's see, I will not see you on Thursday because, remember, Thursday I'm having surgery done on my foot. So I will have a video all ready for you guys. And, you guys just go ahead and watch that on Thursday. Have a great break. I will see you guys once we get back in January. All right, take care.